All right. 5, 4, 3, 2, 1. Locked. Okay. What do we have? All right. So we have an interesting smattering of answers. Who's convinced that they're right? Who's convinced they're wrong? Okay. Okay. Let's have a look. Okay. So, what is the procedure that we need to follow? What do we need to do first? We draw a box around the largest group of ones that we can, right? And what's the largest group of ones? In the center, there's a 2 by 2 group of ones. Yes? And so I can do something like this, right? That should be the first thing that jumps out at you. So what is this? So what are the variables that don't change between all these cells, all these terms? So you've got b equals 1 and d equals 1, right? Yeah? So then this is BD. So the correct answer should have BD in it. Wow. That's good. Okay, what next? Someone, how about, who's not looking at me? You and the New York cat. What would you go next? Out loud? The top one? Which one? The top left one? 0, 0, 0, 0, and just by itself? Or which one do you want to pair it with? Did you pair it with anything? The top two. Okay, so you got these two together. All right, so what variables don't change here? A equals 0, B equals 0, and C equals 0. So this is A prime, B prime, C prime. Okay, so we've got A prime, B prime, C prime in these two. Okay. What about this last little one over here? Should I do this? Yes? With the top one? With the top left, how can I do that? Pac-Man, that's it. Remember Pac-Man. Yes. So this bottom left one is connected to the top left one because of Pac-Man. Okay, so what is the term that comes out of... What happens if I don't do this? What would I get if I don't do this? I get A, B prime, C prime, D prime, which would be this one. You'd go, yoo-hoo, and you'd be wrong. Okay, so that's not minimal. It is a sum of products, but it's not minimal because you have one extra term. So if I did this, then what would this be? What does not change? B equals 0, C equals 0, and D equals 0, which is B prime, C prime, D prime. Yay! So it's this one. The answer's B, right? No! It's also C, somebody says. Ah, very good. Okay. So, how is it also C? Don't rub everything off. Well, you know that this one corresponds to that. Okay, so the other answer is the case where, so this one is a given. We have to have this, right? Because there's no way we can do this and have a, well, this one is joined to this one. There's no other way it can be joined to this one. The other way we can do this is if we did this. And this is equally valid because all the ones have been circled once, at least once, and there is a minimum number of terms here because you use the same size box. as in the other one. So this one would be what? A equals 0. B equals what? 0. You only got 50-50 chance getting it right. C equals 1. All right. No, B doesn't equal 0. C equals 0. D equals 1. Very good. D equals 1. And this is A prime, C prime, D. Okay? So in fact, both of A and B are correct. And that was a trick question. But the point of this is to illustrate that, yes?
One is more correct than the other though.
Why?
Because in answer C, D is not knotted.
D is not knotted.
So it's one less than not yet.
Ah, very good. Okay. But actually, it doesn't, I would argue it doesn't matter because just because there's one less NOT gate here, you could just tap the same input as BD. So you wouldn't actually need to, and on this one you could just tap the same input as, oh hold on, no. Let me see, oh okay, sorry. You've got C prime, D, no, I think they're pretty equal because these are all common. You've got C's, C primes, B primes, you've got C, D here, so you've still got the same number of inputs with the same number of NOT gates. I believe, but I may be wrong because you caught me off guard with that one. I'll have to check later. But theoretically, these are both correct, okay? And that's the point. The minimal SOP does not always have to be unique. You may come up with different answers, and that is okay for the purposes of ENG1030, okay? Cool. Okay, so what do you do now? You've got this minimal sum of products implementation. So this was from the previous, this is from this previous slide without the don't cares. Without don't cares was this one, I think. Yep. And all we need to do is take in a number of inputs, okay? A, B, C, D. Strictly, you probably should have NOT gates going into all of these AND gates. Strictly, we should draw the inverse, but it's often convenient just to put, okay, we're putting B prime, C prime, D, because we don't like drawing lots of triangles and circles. Okay, so you've got a row of AND gates, sorry, a column of AND gates and all culminating into an OR gate. And if I wanted to turn this into a NAND gate implementation, what would I need to do? Replace everything by a NAND gate, and that would be a very simple implementation. Okay, so it's really, really simple. You've got a truth table. How you get to that truth table, we'll talk about shortly in the next section. And we turn that into a Carnot map. A Carnot map gives us this expression, and this expression turns us into logic implementation. Okay? That's pretty much the general process for creating something that you can use to do something, which we'll show very shortly. Okay, so here's a procedure summary. This is more for your reference. I won't take the time to go through all this, but okay, so when you come to study for your test, and also when you want to construct a Carnot map and minimize it, this is a pretty good pre-baked procedure for you to follow. Okay, so you've got the truth table, transfer the data, biggest rectangles. Rectangles must be in powers of 2. Use the don't cares if they make the rectangles bigger. Reuse the ones if it's useful, but they only have to be covered once. And then turn this into a logic circuit diagram at the end. Okay, any questions? No? Okay, let's move on to examples. All right. Discard this. Here's the examples. Nope, that's not the examples. This is the examples. Okay, so I'm going to give some use cases of actual pieces of actual computers that you want to create, really simple ones. So here is a very, very simple computer. It's called a full adder. You might guess what it does. It adds two numbers together in binary. Okay, so over here are two full adders. So here's full adder number 1 down the bottom, and here's full adder number 2. And what each of these full adders does is it adds two single binary digits, two single bits, if you will. A bit represented by A and a bit represented by B, and it gives you two outputs. A sum represented by S and a C out represented by, well, a carry out represented by C out. In addition, it can take one more additional input, which is a carry in. Okay, how is this related to maths? Well, if we have a look at this little arithmetic diagram here, if I have a number represented by A1, A0, okay, and that means this could be 0, 0, 0, 1, 1, 1, oh sorry, 1, 0 or 1, 1. These are all numbers, right? These represent numbers 0, 1, 2, or 3, right? So what we're saying is that if I have two numbers here, represented by A1, A0 and B1, B0, I should be able to give a total sum of those two numbers using binary addition and a carry out. So the carry out is the carry over if I add two ones together or three ones together. So the way you design this is you design a circuit that does it for one bit, and then you can cascade them. So over here, this first adder adds the bits A0 and B0 to give S0 and also gives you carry out, which puts into another identical module where the carry out is connected to the carry in of the next module. And then the adder will add bits A1 and B1 and the carry out from the previous stage to give me another output, carry out 1 and S1 here. Okay? And this is a basic computer. If I want to add two numbers, I convert them into binary, and I put the corresponding voltages, 0 or 1, or 0 or 5 volts, depending if I want a 0 or 1 for the binary, into all these inputs. And hey presto, the answer comes out on S1 and S0, what the sum of those two numbers is. That's the most basic computer. So how do we design this? So I've got a great idea. I want to create something that adds two numbers together. I need to now capture that behavior in a truth table. So some of you ask me, how do you come up with these truth tables? Well, you come up with the truth tables by a little bit of logic, if you will, pun intended, coming from what you need to design. So I need to design something that adds two digits, or adds two bits, A and B, and give me a S, a sum, and a carry out. Actually, I might swap these two rows because it makes it easier to read. Okay, a carry out and a sum. So, sorry, actual fact, I need to add 3 bits because we've got a carry in bit as well. So in that case, if I have the 3 bits 0, 0, and 0, what is the sum of all those 3 bits? 0. So the sum will be 0, and is there a carry out? No, so it'd be 0. So I'm determining what the truth table is from the specified behavior. And the behavior is arithmetic addition. What about if I have A and B are both 0, but I've got to carry in? So this will be a 1, right, for the sum, and the carry out will be 0. How about for this case? So 1 for S, and carry out 0. What about here? 0 for S, because I've got a bit plus a carry from the previous bit, and what will this be? A 1. Very good. Over here, you've got what? 1, and carry out 0. Good. Over here, sum 0, carry out is 1. The sum here 0, carry out 1. The sum here? Well, 0 or 1? 1, okay. Because we've got 3 bits. You've got 1 on the sum and 1 on the carry out. And what does 1, 1 represent in binary? 3, right? Okay, so that's awesome. You have now specified your truth table from a described behavior. Now, described behaviors can get pretty complicated. Anything that you can think of, any way you want a system to behave, can be captured using a truth table. Okay? So now we go about minimizing the logic for this. We put it into our Kano map. Okay, so for this one, the sum, we would put 0, 1. I'm going to go a little bit faster because I can. 1, 0, 0, 1. Right? So that would be the Kano map for the S output for this truth table. Now for the carry out output, let's do the same thing. It'll be 0, 0, 0, 1, 0, 1, 1, 1. Are we happy with that? Have I made any mistakes? I hope not. I don't think so. Okay, so from here, let's get our terms. So next step is, from the Kano map, get the terms, or circle rectangles that are biggest size and get the terms for each of those. Okay, so what is this? What are the rectangles of biggest size in this table? 2 by 1. Where's a 2 by 1? I can go from this corner down to this corner, or this corner around to this corner, but I cannot just go from this corner to this corner. Even Pac-Man can't do that one. Okay, so good. I hope I cleared someone's understanding of the wraparound effect, which is the purpose of this. Okay, so I've only got ones here, okay? So that's not ideal, but it happens sometimes. Okay, so over here, this would be A prime, B prime, C. This would be A prime, B, C prime, A, B, C, and A, B prime, C prime. Yes? Okay, so this isn't any better than just looking at the min terms, is it? There's no simplification, there's no minimization of logic here. That's life sometimes. You can't minimize it. What about this one? We can minimize this one, right? We've got a number of 2 by 1s here. How many 2 by 1s do I need? 3. Good. So there's only one way we can do it, and that's like this. So this one would be what? B, C. Good. What's this one? A and C. And what's this one? AB. Okay. So now we've got this table for carry out is simplified. Great. So now what do? Well, so we know that these two things, we know that the expression will be this plus this plus this plus this for the first one, for the S. And for the carry out, we know that it'll be AB plus BC plus AC. Now, you'll write this neater than I will because I don't have much space on the slide. But you need to be able to show that you know what you're doing. Okay, so now to draw this fully, we've got two things here. So here's one way you could do it. You've got A and B and C in. And how many gates do we need? So for S, we need 4 gates. Oh, this is going to get really messy. All right, so 1, 2, 3, 4. And for C in, we need 3 gates. 1, 2, 3. And we know that for a sum of products implementation, they're all going to go into OR gates, yes? And it's going to look something like this. Okay, blah, 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 blah. And what do we do on the inputs? All right, so this is where it gets tricky. So what I would suggest we could do is we could put one inverter here, and then we get A prime off this, one inverter here, and you get B prime off this, and one inverter here, you get C in prime off this. So C in prime, B prime, A prime. Okay. And now what we can do is, okay, I'm going to attempt to be neat. See how this works out. Okay. Oh, no, bugger it. I'm not going to be neat. Okay, so we've got A prime, B prime, C. So you've got A prime, B prime, C. Yes, it's going to get. I think you can tell how this is going to end up. We've got A prime, B, C prime. A prime. Yeah, change color. Yeah, could do. No. A prime, B, and what was it? C prime or C? C prime. All right. All right. I'm not going to do all of it. You get the idea. Because it's going to get way too messy. But in actual fact, that's how messy it can get if you haven't structured or know what you're doing, but you will know what you're doing. And what I suggest you can do is, if you have a ruler, which I don't, you tap these all off, right? Tap these all off like this. Yeah? Okay. Make sure you got dots on where you want to clearly indicate what's joined to what. I think that's joined to that, that's joined to that, that's joined to that, that's joined to that. And then you can tap off these lines. So I think the first one was, or whatever it is, if it was A, B, C, I've forgotten what it was. You can put A there, you can put B, and you could put C in here, for example, if you wanted A, B, C. And it's a lot neater, right? So you got a ruler, you can do that. I don't have a ruler, I can't be bothered. I'm just demonstrating a concept. Okay, so that is what you would put inside a giant box, which you would then, you'd say, hey, cool, I've now made a full adder. All right. So that's actually what's inside this box that we've gotten here. Okay? So you've gotten A, B, C in, and now you've got C out and S. And you can take, in fact, a number of these boxes. You could take 32 of these boxes and cascade them one after the other. So you could put C out to another one over here, and so on and so on. And you could make a 32-bit adder. And that 32-bit adder could take two 32-bit long numbers, add them together, and give you an output which is correct, hopefully, depending on how well you designed it. Okay, cool. So here's another one. Here's another example. Now here's one you probably wouldn't have heard of. It's called a multiplexer. Okay, sorry, I presume. Who has heard of a multiplexer before? Okay, good. Nobody's heard of a multiplexer. All right, a multiplexer is sometimes also referred to as a mux. And essentially, what it is, it's a switch. Okay, it's a digital switch that changes, well, it switches basically the output, O, to be the same as whatever the input is at A or B, depending on what I put at S. Okay, so and this process is called multiplexing. Okay, so the behavior that we want is if I say S equals 0, and S is selected because it's short for selection or selects. If I have S equals 0, then I want the output. So if S equals 0, I want O to be equal to A, whatever the bit on A at that time is. Okay? And if S equals 1, then I want the output equal to B. Okay, so what this is a little switch that changes its output depending on S to whatever the inputs on A and B are. So that's the behavior that I want. There's no mathematical explanation for this behavior. It's something that we dreamed up that we want a computer to be able to do. We find it useful. Okay, so how would I go about doing this? So I've got S for my select. I've got inputs A and B. So I want if S equals 0, I want the output to be A. If S equals 1, I want the output to be B. So what do I fill in on this truth table here? So S is 0. What's the output supposed to be? 0. Next. 0, 1, 1. Very good. So anywhere where S is 0, I just replicate A. And then if S equals 1, I want to replicate what? B. Okay, so this will be 0, 1, 0, 1. All right. So now let's take this, put it into our Kano map. So it'll be 0, 0, 1, 1, 0, 1, 0, 1. Cool? All right so far? Okay, so what's the largest box I could use, and how many of them? 2 by 1? And there are how many of them? 3. Okay. Let's have a look. So there are 3 of them. I could do this one, and this one. All right? Do I actually need this one? No. Very good. Okay, the reason I don't need this one is because all the 1s are already covered if I have done both of these 2 boxes. Okay, so what's this box? This will be S prime A, right? And what will this one be? S B. Now, if I had put that in, if I had put this one in, what would that be? That would be A and what? B, right? So basically what I'm going to tell you is you can prove that this isn't quite correct, because if you decide to do something like, so if I had S prime A plus SB plus AB, I say that you could simplify this using Boolean algebra simply to S prime A plus SB. And hence, this one is not minimal. Now, it's a little bit unclear how you would go from this one to this one, and that is one of the disadvantages of using Boolean algebra by itself. And that is really why we like using Kano maps, because you can see visually that I don't need this green one because, oops, I need that one. I don't need the other green one, AB, because all the 1s are already covered, and AB is just redundant. Okay, so how do we implement this in a piece of logic using logic gates? So we've got S prime A and SB. Well, here, what would we have? So we would have an OR gate, and you have 2 AND gates, and you would have, I've got S here, I might have S prime, and I've got A here, I've got B here. Okay, I'm just doing like that. Okay, so I would have S prime A, S prime A, and S B. Where's B? be. Okay? And I've drawn this box outside a little bit like a, well, it is a trapezium, because that is actually the symbol for a multiplexer. Okay? So if I was drawing a symbol like a symbol for an op-amp, you know, is a triangle with some pluses and minuses on it. A symbol for a digital multiplexer is actually a trapezium where you've got the inputs on the large side and the output on the small side. Okay, great. So now you've got a little, you've got little components for a computer that can add and it can select inputs. Okay. That's all. That's not going to go much more into those little components. I'm going to go straight into a system example. Okay, so here is a system where I now have two components. I've got this component, which is called a 7-segment display. 7-seg display, and you will use these in your laboratory. I think Lab 5, you'll be using them. Okay, on those, and they're built into the little digital board that you've got there. And this 7-segment display is pretty much like, well, exactly the same as those digits that you see on the clock over there on the side of on the wall. So they will show you a number depending on which segments of the display are lit up. So, and we've enumerated the segments by A, B, C, D, E, F, and G. And depending on which segments you, ooh, what did I do there? Okay, depending on the segments that you light up, you can display different numbers. Okay, so they're down here. You can display 0, 1, 2, 3, 4, 5, 6, 7, 8, all the way up to 9. And just for fun, there's a couple of segments for certain numbers that we can say we don't care about. So for example, on the number 6, if segment A doesn't light up, right, it could light up or it doesn't light up, we don't care, because you could still see that the number 6 is what's meant to be put out on this 7-segment display. Similarly for 9, you could still see what's on the display even if this segment D, this lower segment here, D, doesn't light up. So just for fun, we can say that those are don't cares. Over here, you're asked to design a piece of circuitry that converts a 4-bit number. So 4 bits can represent how many different numbers? 2 to the 4, which is 16. 2 to the 4 is 16. All right, so it can represent 16 numbers, but there are only 10 digits. So we'll only use 10 of those codes. And the specification says that we want to represent a number by its binary equivalent. So the number 0 would be equal to 0, 0, 0, 0. The number 7, for instance, would be equal to 0, 1, 1, 1. Number 9 would be equal to 1, 0, 0, 1. Okay? So these are the inputs on D, C, B, and A. And on the outputs, there are 7 outputs. Each of these outputs must be a 1 if, so for example, if I put in the digit 0 into the decoder, our BCD to 7-segment decoder, then I need certain lights, certain parts of the display to light up. So if I put 0 in, I need A to light up, B to light up, C to light up, D to light up, E to light up, and F to light up. Does that make sense? Okay, so that's your design specification. Okay, so A will only light up for certain numbers, B will only light up for certain numbers, C will only light up for certain numbers, etc. Does that make sense? Okay, so here I have filled in already which segments should light up for which numbers. And I've included the don't cares for 6 and 9, just for fun. So what you would do, and I'll just do it for one of them, I won't do it for all of them, is you would look at DCBA, or the capital DCBA, and then you would look at which segment should light up, and you would put this into your Kano map. So for A, I would be putting in everything down this column. So it'll be 1, 0, 1, 1, 0, 1, don't care, 1, and 1, 1, 0, 0. Actually, what could I put in? What could I put in here when the output goes out of range? So, sorry, when my input gets bigger than 9, I can put a whole load of don't cares in here, yeah? Because I'm gambling that none of these additional codes, DCBA, will ever come up like anything greater than 1001 cannot occur. So that's why I'm gambling that I can put a whole lot of don't cares in there. If they did occur, what do you think would happen? You'd get something weird on the output, yeah? So using don't cares helps because it helps you to make bigger boxes. So for example, over here I can make some really nice big boxes. I'm going to make a big box here. I can make a big box here because of all those don't cares. I can use don't cares here to make a big box, and I can use don't cares here to make a big box. Right? That's great. But if you do happen to get a code or an input which is out of what we've specified, your outputs will start to get a little bit weird. So good practice would say that you should design for what should happen on the output, even if you don't expect to get those inputs. Anything greater than that, you should still design that.
Like say like all zeros or something.
Yep, so you could set it up so that it's all zeros or something, so anything out of range, the display goes blank, for instance. Then you could set everything to 0. Okay, so that would be good design practice. Now I'm not going to fill in all of these because that would take too long. You will be filling in all of those for Lab 5. Okay? And also, there's an extension in Lab 5 which says, well, if you go greater than 10, or if you go 10 or greater, let's start using hex. And you can display hex on these 7-segment displays as well. All right, so that's pretty much it.